Welcome back. Today's lesson is about exponential functions, specifically exponential growth and exponential decay, and we can find this in our book in chapter 7-1. Alright, our objective for today is to be able to write and evaluate exponential expressions to model growth and decay situations. Our vocabulary words are these: exponential functions, base, asymptotes, exponential growth, and exponential decay. I've got them highlighted in the text, and I'll also make mention of it as we're discussing these things today. Alright, let's get started. Alright, growth that multiplies every year can be modeled using a function with a variable as an exponent. This type function is called an exponential function. And you can see it. It is basically the f of x equals b, which is our base. That's another vocabulary word, with x as our exponent. So we've got two vocabulary terms right here. Alright, so this is our basic formula. And for today's lesson, b is always going to be bigger than 0, and it is never going to equal 1, at least in today's lesson. Alright, let's look at an example. Alright, here is the graph of the f of x equals 2 to the x power. So that means for every time x increases, the exponent for 2 has increased. So in an exponential function like this, every time x goes up 1, we're going to multiply by another 2. Well, let's look at the table. When x is negative 2, I've got 1/4. Negative 1, I'd multiply by 2. That gives me 1/2. And that pattern continues. Times 2 is 1, times 2 is 2, and so on and so forth. You can also see that in this graph. Every single time I go up one value for x, my value doubles. That is a typical exponential function. Alright, now let's look at this going backwards. Notice my red line, as my x gets smaller, my graph approaches the x-axis. It's getting closer and closer to 0. But the value of 2 to the x power will never equal 0. This gives us what we call an asymptote, and that's our third vocabulary term. An asymptote is a line that the graph of a function never crosses. It'll get extremely close, but it never actually crosses my y equals 0 line, my x-axis. So that's what an asymptote is. Alright, now let's talk about exponential growth and exponential decay. We'll start with growth. Alright, first thing you need to know, same basic formula. The f of x equals a, which is just some constant, times b, that's our base, to the x power, that's our variable. What's important here is, of course, a has to be bigger than 0, but b, and this is the important part, is bigger than 1. That's what causes exponential growth, and this is a graph of that. Just remember, growth typically means you get bigger. As x gets bigger, so does our y. Alright, now how do we know this? Well, say our base is 2. Every time the exponent increases, we're going to multiply by 2 again. So 2 times 2 would be 4. Is 4 greater than 2? Absolutely. Alright, now let's look at exponential decay. In exponential decay, same basic formula. F of x equals a times b to the x. But in this case, b is between 0 and 1. Like I said, this is called exponential decay. And what's going to happen, since b is less than 1, every time you increase the exponent, you're going to make it smaller. So notice how the graph decreases. Now let's put some numbers to it to help it make sense. Say b was 1/2. 1/2 times 1/2 gives me 1/4. Is 1/4 smaller than 1/2? Absolutely. So remember, exponential growth, b is bigger than 1. Exponential decay, b is between 0 and 1. Alright, just a couple of notes to remind you of stuff. In the function y equals b of x, y is a function of x because it depends on x. Y is the dependent variable, x is the independent variable. Also remember that a negative exponent doesn't make the value negative. It just means whatever that is, whatever the base is to a negative exponent, goes into the denominator. So x to a negative 2 power doesn't equal a negative x squared. It equals 1 over x squared. You might want to remember that. Alright, let's look at this. Can we tell whether this function shows growth or decay? And then can we graph it? Well, for growth or decay, all you have to do is look at the base. The base is 3/4. That's less than 1. It's a decay function. How do we graph it? We'll just make a table. And it does decay. It gets smaller. Now this is kind of gross, but when you think of stuff decaying in the woods, it's slowly disappearing. Well, that's exactly what's happening on this graph. Alright, different problem, same question. We got 100 times 1.05 to the x. Is this growth or decay? Let's look at the base. 1.05, bigger than 1. That's a growth problem. Alright, let's graph this one. Growth, yep, it's getting bigger. That's a growth problem. Excellent job, y'all. Alright, one more thing we need to learn. This right here, the a of t, which is going to be our final amount, equals a times 1 plus or minus r to a t power. Now what does this formula tell us? It lets us model growth or decay by a constant percent increase or decrease. So what that means is, if my r is positive, then whatever I have is going to grow a certain percentage every year. If it's negative, it's going to decay a certain percentage every year. We can use this with mortgage payments. You could do this with investments. There's all kinds of things using this formula would be good for. But since it is just a formula, let's look at a problem that uses it and see what we can figure out. Right here it says Clara invests $5,000 in an account that pays 6.25% interest per year. After how many years will her investment be worth $10,000? Well, first let's work on making a formula. Alright, we'll write out the generic formula. F of t equals a times 1 plus r, since it's growth, to a t power. We plug in the numbers they give us, and we simplify. So here is our formula. Well, that's all we know how to do so far. In a minute, I'm going to show you how to figure this out on your calculator so we can find out when it's going to equal 10,000. And in the next couple of days, I'll show you how to do that mathematically. Alright, let's look at the calculator. Alright, if I plug in our formula into the calculator and graph it, I can use the trace button and use my arrow keys to change my x. And I'm looking for when my y value crosses from 9,000 to 10,000. And whatever that x value is, that's going to be relatively close. Alright, let me show you another way on your calculator. Plug in the same equation, this time hit the table. Now, go down and look. Here at 11, it's 9740. At 12, it's 10349. Somewhere between 11 and 12, our value hit 10,000. So this gives